Hello everyone, this is a talk about our latest work, WebAssembly Decompilation with Inter-Procedural Type Recovery. It's about turning low-level code, WebAssembly code, back into readable C code. So first, let's talk about what is WebAssembly. WebAssembly is a widely used bytecode. It is compiled from C or C++, Rust, Go, and more programming languages. It can be executed fast. It has near-native performance. It is also recently widely used in containers, serverless, and IoT devices. And it's quite similar to binary code in the sense that they also all have unified memory, which compiler will divide it into data section, stack region, and also heap region. It also has some differences from binary code. It has a unique feature called structured control flow. This feature is unique. You will not see it in any other programming languages or virtual machines or architectures. We'll get into that later. So let's talk about what is decompilation. Decompilation is about turning low-level assembly code back into more readable source code. For a typical binary code, it's really just a bunch of binary bytes, and you even need to find code regions, and after finding code regions, then perform disassembly, then recover assembly functions. But these steps are not needed in WebAssembly. In WebAssembly binary format, the function is directly available, and the instruction is explicit. However, other following steps are quite similar compared with native binary decompilation. The high-level types are lost, and you need to recover high-level types using type recovery. After that, you need to do control flow structuring to recover those things like if statement, for statements, and while statements. And finally, you get the readable C code. However, existing WebAssembly decompilers are still unsatisfying. For example, there's a tool called NotDec. It has many stars on GitHub. However, it produces low-level C code, which is very verbose and has poor readability. As you can see here, it has 60 local variables. I can tell you that in the source code, it has only several local variables, which is far less. There is also other some operations that is not exist in the original source. You can see here it subtracts the global variable 0 by 64. It is actually low-level stack pointer operations. In summary, it is much longer and has much less readability. As for the popular decompiler IDA, it only supports disassembly, not decompiler for WebAssembly for now. There is also an effort from community. They developed a plugin that makes Jira support the decompilation of WebAssembly. However, it is still quite buggy and not maintained, and all these decompilers actually lacks a good type recovery. So why is WebAssembly decompilation hard? There are three challenges. The first challenge is to handle the operand stack feature. This feature hides the use-defined relations between instructions. For example, here in WebAssembly, it is possible that if you take one branch, the value on the operand stack will be popped automatically, like here. But if you do not take the branch, the value will not be automatically popped. This is a confusing point when I just started to learn WebAssembly. Another challenge is the low-level operations. For example, there are raw stack pointer calculations, and they access local variables by using the raw stack pointers. What's worse, The third challenge is that there are no high-level types. There are no high-level objects. There are no array access. There is no field access. These accesses are in the form of address calculations. What's worse, these address calculations are mixed with integer calculations. As you can see here, there is an addition statement, addition instruction, and you have no idea whether it is a point or arithmetic, probably calculating the address of a field of an object. However, it is possible that it's just a simple integer addition. So, in overview, our approach has 3 steps. We follow the typical architecture of a traditional compiler. In compiler, there are front end, middle end, and back end, and we also follow this architecture. In the front end, we need to handle this operand stack feature. As you can see in the design document on the top right here, in the design document, it says WebAssembly is designed to decode it directly into a compiler's SSA form. So our solution is to transform WebAssembly into SSA form. SSA form the full name is static single assignment form. It is really good form because it makes data flow explicit. It makes define use chain explicit. So how do we do this? We extend the type checking algorithm, which simulates the stack. After using this algorithm, we can transform WebAssembly code into LLVM IR. We emphasize this thing because if you would like you are also doing research on WebAssembly, you can really consider just transform those operand stack into explicit SSA form, which makes all downstream analysis easier. In the middle end, we need to use compiler optimizations to transform those messy low-level code into one cleaner form. In the binary low-level code, the instructions may be messy, and there are many possible combinations of the calculations to do the same calculations. For example, here you can use add instructions, you can also use sub instructions, but after optimization, we can just match this single form because other forms will be transformed into this form, and so simple pattern is already enough. This makes our code cleaner. After that, we need to recover high-level types. Another point that makes our compiler much simpler is to use a unified type recovery for stack and global and heap region. We reuse an existing type recovery algorithm called retyped. We will not get into detail here. After that, we will recognize the internal structure of the stack region and here, and then we split the structure into individual local variables. In the backend, we need to generate readable C code. And because the time restriction, we will not get into further detail here. As an evaluation, as you can see on the top right corner here, our tool achieved a higher recompilation successful rate, and we are still improving the robustness. There's another baseline called NotDec. It's a large language model-based decompiler. As you can see here, it has actually lesser line of code, which means that their results are more succinct. But however, their output suffers from hallucination issues. As you can see here, there is one branch in the original source, and in the decompilation result of NotDec, the condition is inverted. There are also other function calls that actually in the wrong sequence in the result, and there are some hallucination statements, and there is another baseline called WebAssembly, and we have introduced it earlier. Its result is too verbose and has much poor readability. We also perform evaluation on larger real-world programs. Initially, we found that our inter-procedural type recovery analysis is too expensive. As you can see here, it times out on many large programs more than 24 hours. So we restrict our type recovery to each single function, and we decompile each function individually, just like other decompilers do. In this setup, our decompiler is actually much faster. As you can see here, the average time is lesser, and we use much less memory here. There is a case study showing that we can recover custom data structures, and we can recover field accesses. As an takeaways, the first insight I would like to emphasize is that WebAssembly's operand stack value is actually SSA value. If you lift it into LLVM-IR or other SSA-IR, it is actually much easier for further analysis. Another insight is here that about developing a decompiler. You can leverage existing compiler optimizations and use unified type recovery for both stack, for global variables, and for heap regions. And finally, you can have a much simpler decompiler design with much less heuristics. You can have a full-fledged decompiler with much less code. So thanks for watching. If you have any more questions, just send me an email. Thank you.